Okay.
Okay,
Yeah.
so we're going to begin our session of this Lunch and Learn, and we have a couple of goodies for you guys. Okay, so this is the agenda and also the objective of the Lunch and Learn. This comes from the OMLDS, Orlando Machine Learning and Data Science Meetup, is to provide a space to OMLDS members to share situations, code, knowledge, etc., experience, mainly in the data science field. So we're going to have some introductions, okay, at least, the host. We're going to give you the link for the Discord channel. If it is your first time here, please, join us in the Discord channel. Tell us a little bit more about you and how can we help to enhance your skills and your path into this field. Then we're going to start with the end-to-end machine learning that we just started a couple of months ago. There's some recordings already there if you are joining us today. But we have an update on the GitHub repo, and I'm going to show you some of the highlights of what the repo contains. And then Ron is going to take it to discuss a feature engineering process to calculate distances using GPS coordinates, which is a very useful tool. If you have coordinates in your data set, then you can do distance calculations and create that feature. All right. So first, some of the introductions. I'll start with me. My name is Ricardo Serrano. Nice to meet you. And my regular job is not really in data science. It's more in appraisal. Okay, I do real estate appraisals, also machinery and equipment, aircraft, power boats, etc. But data science is something that I have been looking for, to make like a career change. Okay. Hopefully, that's a good decision. Right now, I know it's a little bit tough, to get into crack that nut, but still, we're persevering. So, and I have met, a whole, a lot of great people, in the R community, Python community, Julia, etc. And I live in Orlando. I'm originally from Puerto Rico, and that's basically it in a nutshell. Ron, take it over.
Sure. Thanks, Ricardo. I first met Ricardo through Orlando Machine Learning and Data Scientists. So we both joined around the same time in early 2019, and we got involved in a volunteer project that was helping the local foster care agency do some machine learning. And since then, around the same time, I actually started my own company called Adventurous Analytics, a consulting company in data science and data management. And I have a background going back many years. Prior to going out on my own, I ran a small IT department, doing all sorts of, basically wearing all different hats in that role, but managing an IT team that did a lot of data management. My educational background is actually industrial engineering, and I also have an MBA. So I'm pretty well grounded in statistics, which is what a lot of machine learning is focused or based in. And I see Jerry just joined us also. Good to see you again. Long time no
Good to see you, Jerry.
Yeah, so it's good to see you guys. I had trouble getting in, but I'm here.
Oh, okay.
Oh,
but you got in.
Yeah, Joe,
we have the waiting room, and I was talking, so I didn't see you for a few minutes there. So sorry about that.
I had trouble extorting the link from the meetup site. So I'm here. Thanks a lot. Good to see you.
Okay, Jerry, just give us something for the audience.
Oh, I don't know. What do you want? I don't sing or dance.
Who are you and what are you doing?
Oh, okay. My name is Jerry Reed, and I teach computer programming, computer science at Valencia College, down in Metro West. And I'm a long-time interest in data, big data. I'm notorious data hoarder. I've during the partial eclipse of the sun on Saturday, I actually collected some solar brightness data and drew a graph of it, and I could actually see the light curve and all
Interesting.
that. So,
Nice.
so I do that kind of geeky stuff in addition
Yeah.
to teaching.
Yeah. I mean, this Saturday was an annular eclipse. I don't know if you guys
Yeah, it was annular if you were out in like Texas. It was
Right, right.
partial here. My neighbor went out to see the annular eclipse, and because
Okay.
he lives in Texas, and
Right.
I'm waiting for him to get back home and show me what he got in terms of pictures. But even here, it was 40–50%. And
Mhm.
although it's not really all that visible to the naked eye, if you measure the light curve, you can definitely see the effect. So
Right.
I'll share
Right.
that at some point. Thanks, guys. Good to see you.
Also talking about eclipses, there's a big one next year. Okay. There's a
Yeah,
total eclipse
April of
next
next
year
year.
that's going to go from Mexico all the way through the United States and Canada. So
Yep.
if you want to see a total eclipse, this is your chance.
It's the last one in the continental
Yep.
US for a long time.
For a long
Now or
time.
never.
So now
I
is
saw
your
the
chance.
2017 eclipse, which was very full eclipse with total eclipse, which
Yeah.
was very nice.
I watched that in South Carolina.
Yeah, I was in South Carolina as well. That seems to be
Okay, there you
the
go.
locale of choice. I was in a parking lot of some little technical college up there, and it
I
worked
don't know
out
if
really
you had to
well.
do it, but I had to move because where I was, there were some clouds.
Yeah,
And I have to move to the highway, to get a better,
the
a
clouds
better
cleared
view.
up just as the eclipse sort of
Yep.
started. I was very
Yep.
lucky, and
I know that was something. Anyway.
all right.
Anyway, let's
Okay,
continue.
sorry to interrupt you
Yeah.
on there. Go right ahead with your.
Yeah, but that great to see you, Jerry. You have been, able.
Yeah, I've been really very busy, and I'm crunching right now on a Maker Faire project. So
I bet. Yeah, I bet.
just stopping in to say hi, and I haven't forgotten about the group. I just been
Excellent.
really swamped.
Excellent. Also, Jerry, we met Jerry, in the OMLDS, project that we worked together. So, and anyone, can give us a little bit of background, where you come and what are you doing? Don't be shy.
I'll jump in.
Great.
Hey, my name is Bryce Machino. I actually went to Ron's presentation at SQL Saturday.
Nice.
I learned about the group, so thank you, Ron. That was a good presentation. I enjoyed it. So I work in supply chain design and grocery retail world. So most of our machine learning is kind of basic time series, regression, clustering.
Yep.
As with a lot of industries, there's a lot of move to like kind of real-time data collection on a lot of sensors and things. So some things that I'm kind of interested in learning about are like real-time anomaly detection on machines, predictive, maintenance, those kinds of things.
Right.
There's a lot of data in supply chain. It's constantly going, so a lot to dig into. But interested to learn more about the group.
Well,
All right.
this
Great to have you, Bryce.
this project that we're on here, the data set we're using as an example is the Kaggle data set for fraud detection. So that'll be right up the alley there for anomaly detection. They're all similar in nature as being highly imbalanced data sets.
Right.
Awesome.
So.
Okay. Angel, you want to say a few words? Angel,
Yes.
I invited Angel. He's from the R4DS community, and we are sharing, some book clubs. And I just invited him, and I'm glad he's here.
Yeah, my name is Angel. I'm from Dominican Republic. I'm an industrial engineer. I work as a reporting analyst. And yes, I'm also moving forward to work as a data scientist, most as an appliance one. More maybe related application related to marketing or maybe industrial, because I'm also that's my major.
Excellent. Excellent, Angel. Great to have you.
Welcome.
Okay, so let's keep going. So the Discord channel, this is the link. Okay, it should be working. So let me put it in the chat right there. Okay, so please, join us there because what the purpose is to continue. We just have 1 hour here, and sometimes maybe you have, a little bit of doubts or questions that pop later, and we can do it in the Discord. In fact, there was a member, Tom, that he was having a little bit of trouble accessing the Google Colab. So I'm still, working on a little tutorial, to present to him and other people that can, maybe have the same problem. They can see a tutorial. So that's coming there. But because we have the GitHub repo, you won't need Google Colab, to access the notebooks and the scripts that we are, we are doing together. Okay, so saying that, we're still working on the end-to-end machine learning. As Ron mentioned, we selected a Kaggle data set. For those that are not aware of Kaggle, Kaggle is a Google initiative to provide a space to data scientists, analysts, etc., to practice real-world scenarios. And they have tons of data sets, a ton of competitions, etc. In fact, almost every week I receive different competitions. There's one very interesting about the football, big data football league, and they have, I think it's 100,000 prizes for the first, for the first winners. So that's going to be interesting. I haven't checked the page, but I'm going to do it probably this weekend to see, what's going on there. So for the newcomers, okay, so that's the link. You can see the first link is the page on Kaggle for that data set that we chose, which is how to detect fraudulent transactions of credit cards, okay? And it's kind of a biggish data set. It has around, the whole data set has around 1.2 million transactions. So sometimes, we have to deal with that, maybe sampling, etc. But it's a good practice, to start, thinking big here. Then we have the GitHub repo, and I'm going to show you a little bit about their repo. Also, we have still the Google Drive link that you can access there, the data set, and also the notebook for the EDA that we're doing, the exploratory analysis that we're doing. But as I say, because we have the repo, now you can get access also in the repo. The only thing that you won't get access is the data set, okay? Because it's a big data set, all right? But you can get it from Kaggle in that link, all right? And let me see one more thing. Okay, so Ron found something very interesting. Before, if you see a recording, previous recording of this, I was using a framework of how to, manage the life cycle of the machine learning models, but I was using a one that was, not geared or not tailored to machine learning. So this one it comes from the same organization, CRISP, all right? But this one is CRISP-ML, okay? They have a framework for machine learning. And one of the things that they, change a little bit is that they join the business and data understanding. They join it in one bubble. Then we do the data preparation, the data cleaning, data wrangling. Then the model engineering, which is kind of analog to the feature engineering that we're going to be covering today. Then the model, creation, evaluation, and the deployment, which is the model deployment, and the monitoring and maintenance. And again, the cycle goes over because sometimes there's something called model drift, right? So your models are not going to be valid forever. So things happen like pandemics or recessions or things like that, shock in the society. So one of the things that we should be aware is that eventually we're going to go over again that model, on a continuous improvement cycle. So that was a great founder, Ron. Thank you for sharing. Then in the timeline, we already did the data understanding, which was the exploratory data analysis. You can check the recordings and also the scripts. We are doing, we're in the feature engineering phase. So there has been some features that we have discussed, for example, date features. There's a feature that identifies the transaction if it's online or not, because that's something that in the exploratory data analysis, we are seeing that is something that is, conducive of checking if the transaction is a fraudulent or not. And of course, we're going to do the distance. So we'll see how that goes. Then after that, the next session is going to be the modeling, the fun part, right? Okay, because right now we have the hat of the janitors, the data janitors. Now we're going to have some fun with the data, with the modeling. And we're going to, talk a little bit about scikit-learn, okay, how you can create a baseline, scikit-learn, but we also want to introduce what is called the AutoML tools. And the tools that we're going to use is called PyCaret, okay? It gives you, the whole plethora of algorithms there that scikit-learn has, and then it gives you the best algorithms that are fitting your data set. And of course, we're not going to stop there. We're going to do the deployment, okay? And that's going to be also some fun with MLflow for version control, and also doing a dashboard, using Streamlit or Dash, depending how things go. All right, so basically that's it. Let me see quickly to show you. I have it here, I hope. Let me see. Sometimes this changes a little bit. Okay, so this is the GitHub repo, and you have that link in the chat. So quickly, how is this organized? Okay, the repo. If you go to that link, you're going to do the same thing as I'm, seeing. But then I just want to talk to you about the structure of the repo, how it's structured. So it has a README. This is part of the README, right? It has a folder called data, which usually it has the raw data, but since that file is biggish, you're not going to find it there. But we are going to find in that data, probably you're going to find some process data, when you do the cleaning and everything. And if you do some sampling, then probably you'll see that, okay, depending on how big it is, because there's a constraint in GitHub. I think it's 1 megabyte or something, on the data. Then you have docs, which are, documents, references, manuals, etc., pertaining to the project. You have notebooks, okay, and we created a notebook for the ADA, and Ron is going to present another notebook for the feature engineering. Then you're going to have the source, and in the source, I want to give you a little bit more detail there. So you're going to have 3 folders: data handling, features, and models. In the data handling, you already have a script of the things that we did in the EDA, but you have another folder called utils. So, for example, in Python, also in other languages, what you do is that you kind of modularize, your scripts. In other words, not everything is going to be in one big script. You can reuse some of those functions, so you can use it for other purposes. For example, we have been working on the train dataset, right? We haven't touched the test dataset. So all the things that we did in the dataset, we read the data, we sample the data, we transform the data, we have scripts for plotting the data. All that can be used in the test dataset. And one of the things that you're going to find is that sometimes the test data set is a little bit different from the train. For example, there could be a new column, right? New variable there that is not in the train data set. How do we deal with that? Well, you're going to find out, because when you apply those scripts to the test data set that you apply in the train, they're going to have some errors, right? And you have to find out how your test data is coming. So that's another, thing that you should be aware when you are, deploying these machine learning tools, all right? And then we have another folder for the features, okay? And another folder for the models, okay? Let me see what else here. Okay, so we have here the source, the notebooks. Okay, the notebooks, there's a notebook on the EDA, on the features, like I said, and eventually it's going to migrate. Some of those functions going to migrate to the source folder. Okay, and this files, requirements.txt and requirements YAML, are the ones that you need to create your virtual environment. So for example, if you're working on a project, usually you're going to create a virtual environment in Python so you can isolate those libraries, you can isolate, and they're going to be pertaining to this particular project. So search in, if it's something that you haven't done, yet, or, you need some reference, just search, for example, Conda, create environment from file or whatever, and you will see the command that you need to create that, that environment, right? So if you do that, you don't need to worry about the Google Colab, okay? All right, so I think we're ready for, let me see. Okay, Ron, good. So Ron, I think we're ready for your spiel.
Okay, thanks, Ricardo. I'm going to share here the actual development environment I'm using. Get that up on screen for everybody.
One more thing, okay? When you create that, virtual environment, if you are using a Mac, for example, you can create it from the terminal. If you're using Windows, then you need, the Anaconda prom or terminal. But also, you will need what is called an IDE, okay? A development editor. So we are using VS Code, all right? Because, that was part of what we learned, in the project that we were involved. But also you can use, for example, PyCharm, okay? Because PyCharm is geared precisely for Python development. So check it out. If you are using VS Code, you can use VS Code. If you are new to this environment, then try PyCharm, okay? Or try both. Maybe you have to decide which one, but you need that tool because Google Colab already gives you that environment, so you have to worry. But when you go in manual mode, then you need to choose an ID.
Very good. So yeah, so as Ricardo mentioned, we're both using Visual Studio Code or VS Code, which is a free IDE from Microsoft, and it has lots of plugins, lots of extensibility, and comes in really handy. I use that pretty extensively in my own business also. I really haven't found a need to move out into a different IDE at this point. So within here, I'll just real quickly describe where we are. So we saw the project structure layout earlier. The data folder, you'll notice that I have all of those data files here. They are grayed out, and that's because if you're not familiar, those extensions are listed in the git ignore, and that is a common practice. You don't generally upload your the actual data files into the GitHub repository. But you will need them if you're going to work locally. And those you will pull down from that link to the Google Drive that Ricardo provided in chat. The notebooks folder is where I'm going to be working today, and specifically on this notebook, I'll expand this just so you can see it, feature engineering for distance. And so we're in that bubble in the overall CRIS ML rotation called data preparation, and feature engineering is one of those steps in there. Today, our objective is to take a look at a potential distance feature. And the reason we landed on that is in the original data set, there is a Latin longitude for the buyer as well as the merchant. And that kind of lends itself to this potential for calculating a distance between two geolocation points, and then allow us to take a look and see if that engineered feature that we come up with might have any value in the overall model. I just stated this, we're not uploading those. There's links, so if you download or clone the repository on these notebook pages, there are links embedded there also to help you move through the notebook itself. Let's see. Okay, so I will start walking through this. We're going to just go through our normal set of importing things. And I should note that this is a notebook running inside of Visual Studio Code. So it doesn't require the separate Jupyter web browser interface running separately. So it looks a little different, but it behaves identical. You know, the blocks of code you can embed markup in the middle of it and have that there as well. But it's all inside, and it's running a kernel inside Visual Studio Code. So I find it a very nice and just straightforward way of doing this. We loaded our libraries in. If you are going to be connecting to your Google Drive, the code is in here. You'll have to uncomment that out. And when you run this, you'll need to provide your own credentials to your Google Drive folder to pull in the data. That's where you're going to save it. I have it saved, like I said, locally. So I'm going to load in the data from these files locally. It's like Ricardo said, the trained data set is about 1.2, 1.3 million rows. So that takes a little time to pull in, a few seconds. And then some of the initial transformations that we learned about in the prior steps during EDA, I'm going to apply those to the data set also, and then just show, here's our full set of the training data with all of the columns that came in our converted timestamp there. So the distance feature, as I mentioned, kind of lent the data lent itself to this, as trying to use this as an engineered feature. We have those two sets of Latin longs, and there's multiple ways to calculate distance. I'll talk about further down in this script. We'll get into geocoding and give you some other examples. But for this example, to keep it simple, we're going to use something called the Haberstein formula, which is the distance on a spherical surface. So instead of like straight line distance, a Euclidean straight line distance, it's a curved distance on the surface of a sphere, essentially. And so it's a fairly good approximation for distances between Latin long locations on the world globe. We pull, if you're working in Colab, you're going to uncomment these to pull those libraries into the notebook. Here, I'm just going to do it directly. And then I'm going to make a subset of the overall columns, only the ones we need for the distance information, which includes the transaction number, our target variable is fraud, and then the credit card number, the original Latin long, the merchant Latin long, and then the street address information that was provided in the data set. And then I renamed the Latin long to buyer Latin buyer long. So all of that's happening here. And we look at the LOCS information. So this is just a smaller set to work with, so I don't have to deal with all the other columns for the example here. Next, the library that I'm using for the Haberstein calculation requires the locations to be a tuple. So we need to combine the Latin long into a single tuple paired value. So I create the buyer location, which is the Latin long, and the merchant location, merch Latin long. Again, that takes a few seconds because it's going through the 1.2 or so million records to do that. But it's not too long here. It's about 14, 15 seconds. There we go. Just taking a quick look at that. These are up on the notebook because I ran them prior just to make sure they're working. So here we see those tuples, and they're the combination of the buyer Latin long and the merchant Latin long that we can see over here. And you can see that real quick. And just added the additional fields. Now, to apply a function like this across rows in a data frame, we're going to use the apply method and to do that on something more than just a very simple function, we go ahead and create or define a function that we can call from within the apply. And this is going to apply the Haversine function using the first tuple and the second tuple of coordinates, and then the unit, we're setting that to miles. And I just went ahead and rounded it to 2 decimal places, just for simplicity to keep it, fairly compact. So let's create that. And then we go ahead and apply and create a new column in our data frame called distance buyer between the buyer and the merchant. And so this is where I'm applying that function right there and passing in the columns that we need from buyer location and it's across the row axis. Again, that'll take probably, I think, about 15 seconds because it's applying it to all of those columns or all those rows in the data set. And then taking a real quick look at that, we just get an example of the calculation. So it went through and applied that formula to the combination of these data points and created a distance for us. So looking at that distance, we want to then take a look at how that's distributed. And on first glance, it looks somewhat normal. It's a little skewed to the left there, but overall it looks fairly normal. I'll show you later if you look closer, it's not as normal as we might first see in the histogram. And then the next thing we wanted to do is, now that we've calculated this distance field, does it have any value or do we see any correlation between it and the fraud indicator in our training data set? And just to quickly go over this code, this is just going to use the Seaborn heat map to plot the correlation matrix. But I did find this nice little trick out there on the web to mask the upper above the diagonal on the heat map, which is nice because typically you just have a mere reflection across the diagonal, which can be a little confusing on first glance. And in this way, it eliminates the diagonal, which is more or less meaningless, a correlation with itself. And then it just really makes it easy to see the things that are highly correlated, such as merch lat and buyer lat and merch long and buyer long, which tells us a little bit, we saw this in the prior EDAs, that this information, the fact that the merchant and the buyer's lat and long are almost identically correlated, means they're probably encoding the same information for a model to learn from and may not be all that meaningful to our end goal. When we look at this distance that we just calculated here correlated to the fraud indicator, it's really, really small, right? It doesn't have much correlation to fraud. That doesn't mean we have to eliminate it right now, but it's probably an indicator that it's going to be a challenge to see if it's going to end up in any kind of finished model to be really meaningful indicator. So going through that, like I said, this data set lent itself to a quick engineered distance calculation because we already had latitudes and longitudes in the base data set. But more commonly, when we're dealing with distance and frequently, we might have a street address, a zip code, something like that, maybe the city and state, and we're going to need to take that information and get the geocode for that. And that's where we're going to go next, is to take a quick look at a library that uses, it's based on OpenStreetMap's information, and it's a Python library, set of Python libraries that allows us to do geocoding. So again, the instructions are here. If you go out and pull up the notebook later, if you download or clone the repository, then you should be able to walk through this locally as well. So we're going to import those libraries. We're going to create instances of those objects for use. And I did mention, I think this is based on a guide that Peter Haas published in Medium. This using this service, and he did a really good job of explaining it. The link is there also, so you need some additional reference for that. Definitely follow that link and follow through there. So then, since the addresses are unique or supposed to be unique per credit card number, because each buyer is a credit card number essentially, we don't need to encode the addresses of 1.2 plus million records. We can narrow that down to the unique street addresses that we would want to see. So here I'm taking a subset of the train, just looking at these fields, making a copy, and then dropping duplicates. So in this case, we get all of those 1.2 million plus observations or transactions really boil down to 983 individuals represented in the data set. In the case of the simulated data set, we can't use the full address to do geocoding because they're fictitious. They didn't provide real people's addresses, and that's, you know, a good decision on Google's part, Google's part, but that limits us a little bit from the real world situation. But we can approximate or just walk through this example by using a combination of city and state that are provided and use that information to do the geocoding. And so this is our little sample here of the geocode. So we see credit card numbers, the street address, the city, state, and zip code. And then we combine the city, state into this one field to use to pass into geocoding. And that's the format that this library requires. They don't want a space in between them. And so that's why I put that in that form. So when I run that function on the full data set, even for the 983, because it's a free service from OpenStreetMaps, they limit it to 1 call per second. And even at that rate, you're looking at 20 minutes to run the full set. So I'm not going to do that during our presentation here. And I'm just making a sample of that set of 5 records to show here. But I do have the instructions in here on how to do the full set. And when we go that, it goes out, or we see our sample here. And now we're going to go ahead and apply that geocode class, and it's going to go just grab those 5 records. And we see it's just it's running a little longer than it did earlier.
Yeah. Just a comment, to the benefit of the audience and
Sure.
people that will watch this. Google has also, a service, right? An API to access the Google Maps, etc.
Yes, I mentioned that. I have that mentioned later in the notes also. Yep.
Okay, so I'm getting ahead then.
No, that's okay. It's a good call out. So this is just one, and I'll talk through that again later.
Okay.
So this went out. It actually took longer this time than I've seen it take. It usually takes about 5 seconds for those 5 records, but we might have some heavy traffic, or maybe the fact that I'm streaming at the same time is making those calls. But in any case, we see that come back, and it brings back this field labeled geocode, and it's an object. This is how it's visually represented in the pandas data frame, but the object itself has different properties, and we want to extract the latitude and the longitude from that object for each of those 5. So this I just labeled geocode, city, state, lat, and city, state, long. So we can see that. We put them into their own fields, and let's see. And then we, again, because the distance calculation requires the tuple, we're going to create another location field, which is the tuple of those new fields, and give you an example of the head here. And so we see the 2 new lat and long longitudes, and then the location field, which is just the tuple of them. This is the block of code that if you didn't if you weren't going to do the sample of just 5 rows and do it on the full 983 unique addresses, you can run through this. This is what I did to save the file myself locally. And like I said, though, it will take about, in my experience, about 20 minutes to run through that. Okay. Now, aside from my efforts to use this geocoding library, Ricardo had also gone, and he's more in both worlds. He's got a foot in the R and the Python world, so he likes to toy around with both. He used an R library in R and went out and created a saved file of new home coordinates, again, for that same 983 records. I'm just going to bring in the head here and show how that shows up in that file. And this file is out there for you to download also on the Google Drive location. So these are the fields. He had the city state in the address field, and then the Latin long that he found in his call to the geocoding service. I went in and renamed them, the address to city state, lat home, long home, to buyer city state, buyer city state long, and did that in place, and then created our tuple again, so that we're again all set. Now this is on the full set of the 983 records, but this is just the head, the first 5 records. So we can take that. I'm creating, and in order to merge this back in with our original data set, the columns that we're using are city and state. So, and in this case, we want the space in between the names. So I redefine that name again, putting the space back between them. And we see here, city state, now there's a space in there. This will allow us to merge it back in with the original, the full data set. And now I'm going to use our same distance formula, just passing in our new buyer city-state location, and again, keeping the merchant location. So now we'll have a new distance between the buyer city-state and merchant. And again, that should take about 15, 17 seconds to run. How are we doing on time? Just keeping a look at that. Okay.
Yeah, we still have 15 minutes.
Okay, we're good. We're good. Yeah. And now I'm going to do a comparison side by side of our original distance calculation and the one where we went out and geocoded them with just city state. And on first glance, they look like, oh, wow, there's a big difference. It's not as big as it would look just because of the scale. I suspect that they did some massaging of data in the Kaggle data set because there really aren't outliers. We see almost every distance lies between 0 and roughly 100, less than 100 miles. But when we went out and geocoded it ourselves and then did the distance calculation, we see there's some distances way out in the 4,000 plus miles range here, and so it just looks very compressed. But the overall shape, if we were to eliminate the outliers and zoom in, it looks very similar in this area as to what we see here, with just a long tail out here. And I think Ricardo did a little bit of digging into it when he first looked. Some of these things are locations that might be in Hawaii or Alaska, because they are all US credit card transactions, but there could be distances that place the city and state way out there. And that might be something that we need to consider on how to handle those types of outliers as we move forward. Also, I did a whole different presentation almost a year ago on managing and handling outliers. So that's a whole nother discussion altogether. But just a quick look at that shows us there might be some differences in our calculated geo or code distance based on our calculated geocode rather than the one that was provided in the raw data. So I'm going to once again go back in and pull in the new fields for our correlation matrix here. And this is the original distance between the buyer and merchant based on the Latin longs given. This is the new buyer distance based on the city-state geocoding. they're very similar. This one's actually negative. It's hard to see maybe. So this is very, very minimal correlation. This one's slightly positive. This one's slightly negative. So we still don't see a huge thing. But something that is interesting, and again, this might be because of the outliers, is that when we look at the intercorrelations between the longitude, latitude, and longitude of the buyer and the merchant, remember originally that buyer, the merchant latitude and buyer latitude were highly correlated, same with the longitude, merchant and, but when we look at it based on our city-state one, they become less correlated. We see the longitude is less correlated here, and the latitude with the buyer city-state is slightly, it's still pretty highly correlated, but less. And that also might be an indication of the different scales that you deal with in latitude versus longitude. I think small, if I'm thinking of this correctly, small changes in latitude is a bigger difference on the globe as opposed to longitude. I might have that backwards in my head, but in any case, there might need to be, that might be a reason to look at scaling the information also, and then doing a correlation. So on first,
just a quick comment, Ron.
Yeah.
Go back to the correlation heat map. Also remind you that, you know, because of the shape of the United States, that is more like a rectangular, you know, shape, the whole, you know, 48 contiguous states. The changes in latitude in terms of the longitude, right? The longitude, which is the width, and latitude, which is the height, are a little bit less, right? So you will see less difference in the latitudes, or more difference in the longitudes.
I see.
Okay, because the spread is greater.
The variance is bigger in
So
longitude.
that confirms, because of the correlation, that confirms that definitely there's more, you know, variation in that longitude factor that in the latitude.
Yep.
Okay.
Yep, that makes complete sense also. Okay, so on first look, it doesn't look like they might be meaningful factors in determining fraud. However, we do plan on carrying these features into the next phase of our model building, and to see, because they're, as we'll see as we get into those next phases, different model algorithms have mechanisms built into them for feature selection also. And so we might get into a model and see the ranking of features, and where they don't immediately pop out, doesn't seem likely that they're going to play a role in the final model. They might, and especially once we start eliminating some other factors, that might bubble up as something that becomes important. As I mentioned earlier, without going fully into it, there are other things to consider on specifically the distance calculation. In the real world, and especially in the commercial world, the Google Maps API for geocoding and distances comes into play, especially if we were dealing with actual addresses and wanted to do something like getting drive time or drive distance, as opposed to that haversine distance, which is the spherical distance. There's also this library that I came across out there that is really helpful for just using the zip code. And then I can tell you, in the example we had in the foster care thing, we actually did need to do a distance calculation, and zip code was the level that we had available. So that comes in handy in that location also. I think it is also still based on the OpenStreetMaps data behind the scenes, but it's just another library. So this is an example of that one where it's using the, you know, it's limited to within a specific country because its postal codes are different by different countries. So as long as you're within a single country, you give it a zip code, it'll encode it, give you all of this information. So that's one. Another thing that might be useful to explore with distances is binning. If you might say, you know, 0 to 25 miles, 25 to 50, 50, 75, something like that, and bin them, and then to go through and see if those binned distances have any good correlation to fraud detection, whether groups of of people or identify. That might be something to do. And then we previously did talk about how to show the correlations for categorical features, but I wanted to point out this library, Dython, which does a really nice job of being able to handle categoricals and place them basically side by side. Oops. And so I brought back in the category, which is like point of sale, groceries, online. Those were the different types of categories that were in the data set, then gender, and then job title. So those are all categorical information, and it identifies those automatically for us. And then we can create using that feature. Oops, it's going to regenerate the correlation matrix. Forgot that one took a little longer. While that's still running, it's probably going to pop up while I'm talking.
Usually when you're using Zoom, things
Yeah, okay, there
tend to take a little bit longer, yeah.
So here we go, and this one I don't have the nice eliminate the upper triangle on the correlation matrix. But it's the same matrix, but it includes the categorical fields, and we can see there's a little bit of correlation between that and the is fraud, but then we can use that to take a look across both categorical and numerical values in the data. So that's another tool that could be helpful, and it prints out this.
Also, I noticed that the city also has a positive correlation.
Oh, yeah,
right?
yeah.
Interesting.
With the fraud. So yeah, city has a positive correlation with fraud.
Yep.
Yeah, good call. So something else.
What is indicating is there are some cities that are more prone to to create those fraudulent transactions than others.
Yeah.
Okay?
Yeah.
It has some variance that is distinguished between legit and fraud. Good.
Yeah. And then, as I mentioned earlier, that distance looks fairly normal, a little bit skewed, but if we go in and calculate the Shapiro test on it, the p-value is tiny. It's probably determined that it's probably not Gaussian in nature. The box plot in this case I wasn't able to get a real good picture showing outliers there, but when you use like a QQ plot of it, it's pretty clear. Also, the center of it, it follows the line, but both tails.
Wow, that looks like a snake.
It does. This is probably showing us that this is not normally distributed data as far as the distance is concerned. So just some additional tools as we're looking through and analyzing, and I see we are running up almost on time here. So I'm going to wrap up there and just ask for any questions. Feel free to unmute yourself if you want me to go roll back to anything in the notebook or have any general questions. Feel free. Oops.
Hello. Hey, could you give any detail about how that package calculates correlation between categorical features?
I'm sorry, could you repeat that?
Yeah, could you give a little bit of explanation how that package calculate the correlation between categorical features?
Oh, I can't easily go through that. There are several different methods. But if you go to that library, it does describe all of the methods that it tries. I'm trying to remember some of them. Ricardo, you might have it off the top of your head.
I can help there. Remember that we did the pandas profiling, okay, when we're doing the EDA. There in the correlations, you have, the Pearson, right, which is the numeric one. The one that we're showing is Pearson. Then you have a ranking correlation, which is Spearman and Kendall, okay? But also, they're based on a rank, they're on numbers. Then you have Kramer's V, okay, which is applied to categorical, and there's a, there's a function in terms of ranking and, frequency on how to calculate that. And also there's one that is for general that is called phi theta, okay? Those Greek letters. And you can see it in the Pandas profiling. I don't know if it's included in the GitHub, but I'm going to check and uploaded that report. You should look that report as kind of an X-ray version of all your data set in terms of univariate, bivariate, correlations, missing values, etc. Okay, but it's a good question, Angel, and it's based more on association. Okay,
Yeah.
in terms of how correlated in terms of those category of features they are, okay, which is kind of different from the numerical correlation. But good question.
Yeah.
Thank you. One more thing. I see Tom. Tom, are you there? Hey, Tom. Hey. Were you the
Hello.
one? Yeah, Tom. How are you?
Hi, hi, Ricardo. How you doing?
Yes. Are you the one that posted the Google Colab issue?
Yes, I am.
Oh,
Yeah.
okay, okay. I saw your message, and apparently, you figured it out.
Well, yeah, I guess, but I want to try this method using GitHub. Is
Okay.
this superior, and I'm going to have less problems with this?
Right,
Is
right.
that what I'm hearing? Using
Yeah.
GitHub.
Remember that the Google Colab is just like a preliminary, like the jump start of this. But eventually, I suggest that everyone goes to the GitHub.
Oh,
Okay.
okay. Thanks.
Yeah. Just go to a GitHub. I mean, and you have the notebook there, so you can run it in your IDE also. Okay.
And I saw you're posting about using Python 3.8. Is that essential? Because I think I've got 3.11 on mine. Should I uninstall that or?
Oh, yes.
Anything greater than 3.8 should work.
Yeah,
Okay?
this
Because I believe there's downward compatibility.
you can see in my Conda environment here, this one's using Python 3.11 also for this notebook. You should.
Okay.
Oh, okay.
Excellent.
Yeah.
Because the thing is that 3.7, which is still around out there, is sunsetted. Okay. In other words, there's no more active developing of the Python people in 3.7. It's just maintenance. So you should be moving. If you have 3.6, or forget it, you have to move. But 3.7, you should be moving to 3.8 or higher.
Or higher. Okay, great. Thank
Great.
you.
Excellent.
Okay. And
Okay,
I'm gonna go ahead and stop the recording at this point. Stop the share and stop the recording.
Okay, so one more thing that that we're here, and give you a second minute.